Welcome back to the Deep Dive, where we take a stack of dense source material and really filter it down to the critical knowledge you need. For this session, our mission is precise. We're moving entirely past readable source code and diving deep into how compiled programs actually work, right down to the lowest level. We're going inside the binary file itself.
And this isn't just about, computer science theory. This is absolutely critical knowledge for anyone serious about cybersecurity. Specifically, I'm talking about malware analysis.
Right.
The thing is, the vast majority of malware, the really damaging stuff, is still written in C or C++ blend. So to reverse engineer it, to really understand what it's doing under the hood, you have to be able to read and manipulate that binary structure.
Okay, that sets the stakes perfectly. So before we can even look at the machine instructions, we need to understand the container they live in. Every great analyst has to start with the blueprint. And in the world of Unix-like systems, that blueprint is the executable and linkable format, or ELF.
Exactly. ELF is the universal filing cabinet. It's used everywhere on Linux and other systems for everything. Executable files, object code from a compiler, shared libraries.
Like DLLs in the Windows world.
Right. And even the core dumps you get when a program crashes. It's really the mandatory structure for modern compiled code.
So if ELF is the container, we need the key to look inside. The sources make a crucial distinction here. They say the ELF structure isn't viewed in just one way. It has two distinct personalities. It depends on when you're looking at it and who.
That's probably the most important conceptual hurdle to clear right at the start. The ELF file gives you two primary ways of organizing its contents, and they serve completely different masters.
Let's break down those two masters then.
First, you have the section header table. Think of this as the detailed architectural blueprint. It's for the builder. In this case, the builder is the linker. It lists all the small organizational pieces of the binary, which we call sections.
Okay, so sections are for the development tools for piecing the program together.
Precisely. They're the static organizational parts. Now, the second view is the program header table. This one defines the segments. And this view isn't for the linker, it's for the operating system's loader.
The loader. So this is for when the program actually runs.
Right. When the OS goes to run the program, it doesn't care about all those tiny little sections. It just wants to know about the larger contiguous blocks of memory it needs to allocate, the segments.
So sections are the raw construction details, where the pipes are, the wiring, and segments are more like occupancy permits. This block is for living, this one's for storage. A huge difference in perspective.
It is. The linker needs the precision of sections to stitch everything together. The OS just needs segments to map memory and apply security permissions at runtime. If you confuse those two, you're going to misread the whole execution model.
To make this real for everyone listening, the sources advise a practical approach. You just compile a simple program, like a hello world in C++ SAS, and start peeling back the layers. What's the very first tool we should grab?
Before you bring out the heavy artillery, you start with the simplest thing, the file utility. It's quick, it's generic, but it instantly tells you if you're looking at a 32-bit or 64-bit executable, if it's dynamically linked, and it confirms, yes, this is an ELF file. It gives you that immediate context.
Okay, so we've confirmed the format. Now we can start looking inside. We mentioned this hierarchy. Symbols are organized into sections, which are then organized into segments. That relationship seems key. Let's start with symbols. What are they, fundamentally?
Symbols are essentially labels for your code and data. Function names, variable names, that kind of thing. The symbol table is the binary's internal index. So for example, if your program calls a function like print, it doesn't know the memory address of print at first, it just knows its name.
And the linker's job is to use that symbol table to resolve the name, to connect the dots so the program knows where to jump.
Exactly. And a complex binary can have thousands of these entries. And these symbols, they point us directly into the most critical sections.
Right. So speaking of sections, if an analyst is looking at a new, unknown binary, what are the first few sections they should immediately check?
There are three main functional sections you have to know, and one very important one for storage.
Let's hear the first three.
Okay, first up is the .text section.
.text.
Right, this is the code segment. This is where the actual executable machine instructions live. It's the brain of the operation. It's where reverse engineers spend 90% of their time.
Makes sense. Code goes into text. What about data?
Data gets split up. First, there's .data. This is for initialized data. So if you have a global variable, say int count equals 10, that value 10 lives in the .data section.
Okay, so initialized data.
Then you have .row data. That's read-only data. This is essential. Constants, immutable strings, that hello world string from our demo. It lives in .row data. The OS makes sure that memory can't be overwritten accidentally or maliciously.
So we've got code in .text, mutable data in .data, and constant data in .row data. What was that fourth one you mentioned?
That's the BS section. This holds uninitialized global or static data. And the key thing here is that .bs doesn't actually take up space in the ELF file on disk. It's a placeholder.
A placeholder. How does that work?
The operating system just allocates zeroed-out memory for it when the program loads. It's an optimization by the compiler. Why store a bunch of zeros on disk when the OS can just create them in memory for you? It keeps the binary lean.
That's a great detail. Now, to view all these pieces, we need better tools. The sources highlight two, readelf and objdump. These are the analyst's microscope.
Absolutely, they're foundational.
So let's use them to look at symbols again. This is often where malware hides, right?
Yeah.
If I run readelf on our compiled program, what are the big landmarks I should look for, beyond something obvious like print?
Two symbols are absolutely paramount. You have main, which is where the C++ programmer thinks the program begins, but the actual truth, where the operating system actually starts execution, is the start symbol.
That start versus main difference is fascinating. Why the extra step? Why wouldn't the OS just run main directly?
Well, that extra step, that code between start and main, is often library setup code. It does things like setting up the environment, initializing the global variables we just talked about, preparing command line arguments. It makes sure the environment is clean and ready before your main function gets called.
If from a security perspective?
From a security perspective, analysts often look at start first. Because if an attacker wants to hide some malicious initialization code, they can tuck it in right before the call to the legitimate main function.
That's a fantastic pivot. We've established the static structure, the sections. Now let's see what the OS cares about when it runs this thing. Let's talk segments. What's the critical security feature they enforce that sections alone can't?
Right. This is where we go from organization to runtime defense. When you look at the program header table with a tool like readelf, you'll see a bunch of segments. One for code, one for read-only data. But the crucial one for this discussion, a cornerstone of modern security, is the G and stack segment.
The stack. That's where all the temporary dynamic data lives. Local variables, function parameters, return addresses. It's fundamental.
Precisely. And to see why it's so important for security, you have to think about the classic buffer overflow attack. Traditionally, an attacker would write too much data into a buffer on the stack. That extra data would overwrite the legitimate return address and force the program to jump to a new memory location.
A location where the attacker had injected their own malicious code, their shell code.
Exactly. But now look at the properties of the GNU stack segment. The operating system marks this segment as RW read and write. It has to be. But critically, it's also marked NO execute.
There's the aha moment. By marking the entire stack segment as non-executable, the memory is treated as just data.
That's the enforcement mechanism.
Yeah.
It's often called data execution prevention, or DEP. If an attacker manages to inject shellcode onto the stack and the CPU tries to execute it, it sees that NO execute flag and bam, it raises an exception. The program crashes instead of running the malicious code. It completely neuters that classic attack vector.
That is a phenomenal piece of engineering built right into the ELF structure. Okay, so we've broken down the structure, the runtime security. Now let's look at the actual language the computer processes assembly. We use objdump to disassemble the binary, to turn the bytes in .text back into human-readable instructions.
This is where we see the code, but you immediately run into a syntax problem. By default, objdump is going to show you AT&T assembly syntax.
And if you're coming from really almost any other background, especially Windows reversing, AT&T syntax looks archaic. The sources call out the % signs for registers, $signs for values.
It looks heavy, for sure. The most confusing part for beginners is the instruction order. AT&T puts the source operand before the destination, so if you want to move the value 5 into the EAX register, it's written move $5 %AX. You have to mentally translate it, move 5 to EAX.
And the sources point out that most analysts just don't stick with it. They prefer the other flavor.
That's the Intel assembly syntax. And it's widely seen as much cleaner, it's more logical. The destination comes before the source. That same instruction becomes simply move elecx 5. It reads naturally. Move into EAX, the value 5.
So understanding which syntax you're looking at isn't a stylistic choice, it's mission critical. If you miss that source-destination swap, you completely misread the program's data flow.
Absolutely. It's a great example of why low-level analysis is so detail-oriented. And while AT&T is the default, analysts use tools that let them instantly flip the output to Intel syntax. Readability just saves so much time.
Excellent. So we have the structure, the security model, the language. Let's move to the practical application of all this, modifying the binary. The dark arts, this is essential for patching or for changing malware behavior in a sandbox.
Right. This is the realm of the hex editor. Its purpose is simple but profound. Directly modify the raw bytes of the binary. You're not editing source code anymore. You are editing the data structure itself. The sources suggest using an online one like hext.it. It's just faster and clearer than a lot of the command line editors.
Let's walk through the example from the sources, because this really illustrates the power here. The goal was to take a compiled demo, system.cpp, and edit it to spawn a shell.
Right, so the original program probably called a command like clear to clear the terminal. When you compile that, the ASCII string clear is represented by a sequence of hexadecimal bytes, probably in the BR data section.
So step one is opening the binary in the hex editor and just searching for the ASCII string clear.
Exactly. Once you find those bytes, you replace them with the command you want to run. In this case, to spawn a shell, the analyst needs to replace clear with sh.
Okay, but clear has 5 characters. Shish only has 2. How do you handle that length difference?
This is where that low-level knowledge is key. Strings usually have to be terminated by a null byte, a 000 to hex. So the analyst replaces the 5 bytes for clear with the 2 bytes for shish, which are 7368. Then they follow it with padding and the null terminator. The full sequence will be 73680000.
The 7368 is sh, and the trailing zeros fill the remaining space and make sure the program stops reading the string at the right place.
Precisely. You're not recompiling anything. You are directly reaching into the ELF structure, modifying the data, and fundamentally changing the program's behavior with just a few byte swaps.
That's incredible. The source code is totally irrelevant once the binary exists. Its whole structure is laid bare.
And that's the core takeaway. This level of access proves that at the binary level, everything is mutable. All the high-level language abstractions are stripped away.
That brings us to the end of a packed dive. We covered the ELF format structure, distinguishing between sections for the linker and segments for the OS loader. We identified the crucial security role of the GNStack segment in defeating common exploits. And finally, we saw how tools like objump and hex editors let us read, disassemble, and even modify the machine language itself.
And if we connect this back to defense one last time, remember our discussion about main versus start. Given that malware loves to hide in these structures, here's something for you to explore. How do automated scanning tools decide whether to trust the main symbol or the start symbol to identify where a program begins? And what happens if a skillfully engineered binary tries to manipulate those starting points to hide its true intent from the detection engines?
Something to mull over as you look at your next security report. Fascinating stuff. We'll see you next time on The Deep Dive.